Welcome to lecture 15, NPTEL online certification course on bioreactors. In the last lecture, we had started module 4, which is on cultivation parameters that affect bioreactor performance. We saw a few cultivation parameters or bioreactor environment parameters as they are called that affect bioreactor performance. We will continue on that today. What we saw in the previous lecture was that there are many cultivation variables that impact the performance of bioreactors. The few common ones that are measured and controlled are temperature, pH, medium composition, aeration and agitation, as well as the dissolved oxygen level. We had seen some details of temperature, the kind of organisms, depending on whether their temperature range of growth is narrow, stenothermal, or broad, eurythermal, and whether the organism is mesophilic, depending on its optimum temperature around 30 degrees C, whether it's psychrophilic, optimum temperature 15 degrees C, or a thermophilic, optimum temperature 60 degrees C. Then we also saw the adjective, obligate and facultative, that can be used in many different contexts, including its temperature dependence. Obligate means strict, facultative means flexible. Then we saw a mathematical representation of the effect of temperature. Then we saw the application of low temperature to maintaining cell lines and strains for production and research, for use in sperm banks, as well as to keep whole humans in a state of suspended animation. There was some reference to videos. I hope you have seen them. They are interesting videos. And then we looked at some aspects of temperature control. Then we went on to medium pH. Some organisms can grow well over a wide range of pH, whereas some other organisms, some other cells such as mammalian cells, have a very narrow pH range for growth. So pH needs to be measured and controlled well in the bioreactor to get the best out of the bioreactor. And we also said that pH buffers supplemented with media components cannot be used for pH control. The cells just don't grow in them, probably because of the high ionic strength of such media. Then we looked very briefly at aeration and agitation. Then we said how they could be controlled. We said they keep the cells in suspension, but they also cause shear stress on cells. We said we will look at these two aspects starting in this lecture. Let's go forward. Dissolved oxygen, or DO, is what we are going to look at next. We are going to look at this in some detail. Aerobic cells in culture are in the liquid. They are not in air. Therefore, the oxygen that is available to them is the oxygen that is dissolved in the medium, dissolved in the water, predominantly in the medium. And DO is the level of the dissolved oxygen, and it is given as percentage saturation with air. Predominantly air is the source of oxygen for most bioreactors, and therefore it has been the practice to give dissolved oxygen levels as percentage air saturation. What it means is you would have been introduced to the concept of equilibrium. Let us say that we are considering water which is in contact with air. Oxygen which is in the air will transport to the water phase, the liquid phase, the gas phase. This will happen till there is a certain equilibrium that is achieved. Microscopically speaking, there is a rate at which oxygen molecules move from the gas phase to the liquid phase, and there is a rate at which the oxygen molecules move from the liquid phase to the gas phase. Both keep happening, And at a certain stage, the concentrations are such, the rate of oxygen movement from the gas phase to the liquid phase equals the rate of oxygen movement, oxygen molecule movement from the liquid phase to the gas phase. This is the condition we call as equilibrium. The concentrations, of course, bear a certain relationship that is given by Henry's law and so on when the equilibrium is achieved, but they are not equal. You have 21% oxygen in the air. You have probably about around 8 ppm under standard conditions. In water, oxygen is a sparingly soluble gas. It's only about 8 ppm, 8 milligrams per liter is what you find here when you have 21% oxygen in the air. This is true for any species that is partitioning between two phases and so on from thermodynamics. You would know this. This particular example is, or this particular system is what is of interest in bioreactors. Therefore, we'll look at this in some detail. Right? So, oxygen is partitioning at equilibrium. You have a certain relationship between the dissolved oxygen concentration in the liquid and the concentration of oxygen in the air, given in different units and so on. Now, when it is saturated with air oxygen, you have a certain amount of oxygen in the liquid. If you change the gas phase composition, of course, the equilibrium concentration in the liquid is going to change. If you replace air with 100% oxygen gas, the oxygen concentration at equilibrium in the liquid is going to be very different. It is going to be about 40 ppm compared to 8 ppm when you have air which contains only 21% oxygen. You need to keep this in mind. So when you use air, when it is completely saturated, you say that it is 100% saturated. And we typically work between 0 and 100 in normal cases. Whereas you should keep in mind that when the gas concentration is changed, you can go above 100% air saturation. You can go up to a maximum of about 480%. This is 21%, that's 100% oxygen. If it is completely oxygen that is in the gas phase, then you can go up to 480% air saturation. So this is the bioreactor here again, the schematic of it, the stirrer as we have seen earlier, the medium in which cells are growing, maybe the DO probe, pH probe, the air inlet, and a temperature probe. Let us choose a conceptual system. Our systems, as you know, could be either real or conceptual. In this case, we are going to choose a conceptual system. Why we are choosing such a system would become a little clearer later. Most likely I will point that out. The system that we are going to choose is this broth minus the bubbles, the air bubbles that are going to come out here. The air bubbles are the ones that carry oxygen and provide oxygen to the medium, which the cells in turn take up. We are going to take the broth as a whole, which contains everything, including the gas bubbles, and then we are going to conceptually remove the gas bubbles from it, and that is going to be our system. If we write a balance on oxygen for this system, this is the overall balance equation. We always start here, it's very fundamental. So input rate of oxygen minus the output rate of oxygen plus the generation of oxygen minus the consumption of oxygen equals the accumulation of oxygen, all in terms of mass per time. We have chosen this particular system, broth minus bubbles, so that we could actually set the output rate to be equal to 0. Okay? It simplifies our approach significantly. So the output rate is 0. Imagine this. We have broth minus bubbles. So only the liquid part of the broth is our system. For oxygen to go out of the liquid broth, you need to reach supersaturated conditions. Assuming that we are not going to operate at supersaturated conditions, we will say that for our purposes, the output rate of oxygen from our system, which is broth minus bubbles is our system, the output rate of oxygen from our system is going to be 0. That's how we set this to be 0. There is of course an input rate which is from the gas bubbles to our system, which is the liquid broth. Let us assume that there is no reaction that generates oxygen in our system, and for now let us keep the consumption, okay, and also the mass of oxygen, let us write it in terms of the concentration of oxygen, which is what is usually measured, which is measurable. Therefore mass is concentration into volume, and if we could replace this, we could write it in terms of concentration and so on. Now if the rate of input is greater than the rate of consumption, if you can provide oxygen at a much faster rate than the rate at which it is being consumed by the cell, the accumulation rate is going to be greater than 0, right? It's easy to see here. Ri is greater than Rc, therefore Ri minus Rc is positive, therefore dm dt is going to accumulate. If this is the case, then the DO, the dissolved oxygen level, will increase, right, from balance. Alternatively, if the rate of input is less than the rate of consumption by the cells, then the accumulation is less than 0, so the DO will get depleted, or the DO will decrease. And if the rate of input equals the rate of consumption, then the accumulation rate is 0, the DO will be a constant. It is a steady state situation, DO will be a constant. We strive to achieve this condition while operating bioreactors. The DO set point, this is measured and it needs to be controlled. Let us see what the DO set point is. The constant value of DO that was mentioned just now can be set at different percentage air saturation, percentage DO. When the air, this is what we talked about in detail just a while ago. Let us redo this just to get the point across. When the broth is saturated with oxygen and air, DO is 100%, air contains 21% oxygen. Thus, if pure oxygen is used as the atmosphere, the maximum possible DO would result. That would be about 480%. So this is 21%, this is 100% oxygen. So there would be a corresponding change, because Henry's law, P equals Hx, that P is the partial pressure of oxygen in the air phase, and X is the appropriate concentration in the liquid phase, the mole fraction in the liquid phase, therefore which is connected through the Henry's law constant. And if you work that out, that's a linear relationship. Therefore, the 21% corresponding to 100 means that 100% would correspond to about 480 or so. Now, why we are interested in this? See, DO is nothing but the accumulated level of oxygen in the medium. The oxygen is being taken in by the cells, the oxygen is being supplied through aeration and so on, all those are fine, but the DO actually tells you the level of oxygen in the broth. What has been found is that many aerobic bacteria need a DO above 50% to do well. There are innumerable studies in the literature on the effect of DO on the growth and productivity of many different systems of interest, many different organisms of interest. Many aerobic bacteria have been found to prefer a dissolved oxygen level of greater than 50%. That's why we are interested. But some organisms, Clostridium astrobutalicum, just to be italicized, Clostridium astrobutalicum, which is microaerobic, which requires low levels of oxygen, requires a DO of less than 5%. Now, let us look at the oxygen supply. Before that, let me emphasize, it is because of this that we need to worry about the DO. DO directly affects the growth and productivity of organisms, although it is only a level of accumulation. Now let us look at the details of oxygen supply. I have artistically represented an air bubble by this hemisphere or a semicircle here. They are actually spheres, approximately maybe. I've just represented this by a hemisphere in 2 dimensions, a semicircle. This is the air bubble and this is the cell. This is the liquid medium in which both are present, our system actually. What happens is oxygen from inside the air bubble moves to the liquid and then moves to the cell. In this process, if we look microscopically at this process, and if we look at the concentrations or the mole fractions for that matter, the mole fraction is going to be the highest inside the air bubble in terms of the gas mole fraction. Then here at the interface, this is gas concentration, this is liquid concentration, it is going to be at equilibrium. People have found that it instantaneously achieves equilibrium at the interface, and then all we are concerned with for a while is the liquid phase mole fractions. So XAI, the liquid phase mole fraction, is the equilibrium mole fraction with YAI in the gas phase. Then there is a region very close to the air bubble where the concentration of oxygen decreases quite drastically. The mole fraction of oxygen decreases quite drastically in the liquid, and this conceptual region is called the gas liquid film. It actually doesn't, there is no film and so on and so forth. It's a region, the film is a conceptual point. This is the region where the concentration decreases rapidly, and then in the liquid there is a concentration or the mole fraction XAL. And around the cell, again, because there are 2 phases, cell is some sort of a semi-solid, semi-liquid phase, and this is a liquid phase. Therefore, there is a film around it where there will be a significant drop in the concentration, and the cell sees the final concentration which it takes up for its metabolic needs. In fact, the only place where oxygen is required in the cell is as the final electron acceptor of the electrons released by various substrates in the oxidative phosphorylation pathway. That's the only place where it is required by aerobic organisms, but that's so crucial that it becomes essential. So oxygen needs to be supplied to bioreactors to satisfy that particular need of the oxygen acceptor, the electron acceptor. Let us consider the transport of oxygen across the gas liquid interface when it is at steady state. Okay, let us say that the steady state has been reached and we are looking at the transport across this interface here, right? The rate of oxygen entering the gas liquid interface must equal the rate of oxygen leaving the gas liquid interface for steady state to remain, or for steady state to be achieved. So this is true at steady state. And now let us look at flux, which is, you may have been introduced to this. Flux is nothing but the amount transferred per unit area per unit time, or in other words, it's a rate per unit area. The area is perpendicular to the direction of transport. You would have seen flux, mass flux, momentum flux, and so on in probably your transport course. We will deal with flux here because it is much easier to see things here. Okay? This is an engineering meaning of flux. There is a slight difference in the way flux, the term flux is used in some other context. There is one such context which comes in module 5. I'll point that out when we see that. So the rate is the same, the area is common, therefore the flux of oxygen entering the gas liquid interface must equal the flux of oxygen that is leaving the gas liquid interface. I've just divided these terms by area, which also happens to be the same. Flux can be seen as a transfer coefficient times driving force. This is a standard way of looking at flux. It is seen as a product of a transfer coefficient times a driving force. Driving force is the one that is necessary for the flux to occur. And let us say we call the flux as Na in this case. We will develop it as A and then apply it to oxygen. This is generic species A. The transfer coefficient is Ky, it is the mass transfer coefficient of oxygen. The transfer coefficient in the gas phase is Ky into the concentration difference, that is the driving force here. That's the way, that is this formulation, the transfer coefficient formulation, where it is given as a, where the flux is given as a product of the transfer coefficient and the driving force. So the transfer coefficient Ky is here, and the driving force is the difference in concentration or the difference in mole fractions here, YAG minus YAI. Okay, this is the flux of oxygen reaching the interface. On the liquid side, it is Kx, the transfer coefficient, times the driving force, which is XAI minus XAL, the difference in mole fractions here. So these two must be equal according to the condition for steady state. Let us call this equation 1 because we are going to refer to this equation through this particular development. And the flux needs to be the same, therefore each term equals Na, which we have defined as the flux. The interface concentrations on the gas and liquid side are at equilibrium. That is what we said earlier too. The YAI and XAI are at equilibrium. They are equilibrium concentrations, and therefore YAI can be written as some constant into XAI. From a larger perspective, if you recall the equilibrium curves, it is typically YAI versus, the mole fraction in one phase versus the mole fraction in the other phase. It is usually a curve. So in certain regions, the curve can be approximated to a straight line. That's essentially what this means. We are looking at piecewise linearity of the overall equilibrium curve, and we are taking that to be a linear relationship between YAI and XAI in that small region. Let us call this equation 2. M is the equilibrium constant. This is usually the Henry's law constant. The interface concentrations YAI and XAI are usually difficult to measure. So we need to formulate our equations in terms of measurable or knowable concentrations. This is very difficult to measure. Some people have measured it through some specialized probes when they did studies and established that indeed equilibrium exists there. But we cannot do it on a regular basis. So if we write this in terms of the concentrations that can be measured, let us say that this is some transfer coefficient Ky in the gas phase times YAG, which is the bulk gas concentration. I hope you can remember this. YAG minus something, YAG is here, XAL is here. The overall transfer coefficient YAG minus YA star, and that equals on the liquid side Kx into XA star minus XAL. In a minute I will tell you what the star means. Let us call that equation 3. And each term of course equals Na. Ky and Kx are the overall mass transfer coefficients. What overall means is something like this. This is the individual side mass transfer coefficient, this small lowercase ky and lowercase kx. They are for the gas side alone or the liquid side alone. Whereas if we are looking at a transfer coefficient from here to here, we want to relate the transport, the flux, with these concentrations as the driving force, the gas phase concentration and the liquid phase concentration. We cannot do that directly because this is gas phase, this is liquid phase. The gas phase composition is, let's say, apples, and the liquid phase composition is oranges. You cannot subtract apples from oranges or oranges from apples. So we represent the concentration here in terms of an equivalent gas phase concentration. The concentration in the liquid phase in terms of an equivalent gas phase concentration, and that is what Ya star is all about. This is the concentration that is in equilibrium with the gas phase. At equilibrium, when the liquid phase concentration is XAL, the corresponding gas phase concentration is Ya star. So we have replaced these individual side mass transfer coefficients with an overall mass transfer coefficient and measurable or knowable quantities such as the equilibrium value. Similarly, on the liquid side, it is an overall mass transfer coefficient Kx times Xa star minus XAL. Xa star is the concentration that is in equilibrium with YAG, the gas phase bulk concentration. Ya star is the gas phase composition that is in equilibrium with the liquid phase bulk concentration. Right? So these are not actual quantities in terms of existing quantities, but these are conceptual quantities. They can be measured under conditions of equilibrium, but under those conditions under which transport is taking place, these are conceptual quantities. So Ya star is nothing but m times XAL in terms of the same equilibrium constant, equation 4. Since each term in equation 1 equals Na, equation 1 was this, each term equals Na, therefore we could write YAG minus YAI, Ky into YAG minus YAI was Na, therefore YAG minus YAI is Na by Ky. Let's call this equation 4. And similarly, XAI minus XAL is Na by Kx, equation 5. Equation 4 can be written as, we are replacing this with the liquid side concentrations. M times Xa star is YAG, M times XAI is YAI, therefore M times Xa star minus XAI is Na by Ky. Similarly, Xa star minus XAI equals Na by Mky. We'll call this equation 6. This is just dividing both sides by M. Adding equations 5 and 6, we are doing this so that this is plus Xai minus Xai, we can get rid of Xai, which was indeed our purpose, which is indeed what we were looking for. These are not easily measurable, therefore we don't want our relationships to have Xai's and YAI's. If we do that, Xa star minus XAL is Na common, 1 by M plus Ky plus 1 by Kx, equation 7. Equation 3 can be written as, let us see what equation 3 is. Equation 3 is this, the overall or the fluxes in terms of the overall mass transfer coefficients and the overall driving forces. Xa star minus Xal is Na by overall transfer coefficient Kx, equation 8. Equating the right hand sides of equation 7 and 8, because Xa star minus Xal is this, Xa star minus Xal is Na by Kx in equation 8, in equation 7 it was different. The left hand sides are the same, therefore we could equate the right hand sides. We get 1 by capital Kx is 1 by small ky plus 1 by lowercase kx, equation 9. If m is large as for oxygen the typical value of the Henry's law constant is 4.75 into 10 power 4, which is a large number. If m is large, as you can see, m is in the denominator, we can conveniently ignore this. Okay, large compared to other values, that is. But in any case, if the m is large, the denominator here is going to be large because the other values are maybe of the same order of magnitude, and therefore 1 by a large value can be taken to be 0, and therefore 1 by capital Kx is approximately equal to 1 by lowercase kx, equation 10. And fluxes, as we saw, moles transferred, amount transferred, in this case moles transferred per area per time, so that is Kx into Xa star minus Xl. The mass transfer rate is moles transferred per time. Therefore, we need to multiply this by the area, the interfacial area, because it is the area that is perpendicular to the direction of the flux. So, Kx times A area, interfacial area, times Xa star minus XAL, and therefore the moles transferred per unit volume, these are measurable. Area in the interfacial areas are not so easily measurable. Per unit volume per time is Kx A by V Xa star minus XAL, and the total interfacial area per unit volume is given the symbol A equals Kxa Xa star minus XAL. A is the interfacial area per unit volume, as we just saw. This Kxa times the concentration of oxygen is what is referred to as KLa. You would have come across this term KLa for the bioreactor. This is what it actually is in terms of the fundamental viewpoint. So, the mass transfer coefficient, the overall mass transfer coefficient, this is on a mole fraction basis. This, if we multiply by the total oxygen concentration in the medium, it becomes on a concentration basis, the molar concentration basis. The molar concentration, the mass transfer coefficient of oxygen on a molar concentration basis, and also on a volumetric basis, is KLa. So, it's called the volumetric oxygen transfer coefficient. This is KLa, which you might be familiar with. So, the rate of input, we did all this because we were writing a balance on oxygen. The oxygen is supplied from the air bubble into the liquid. So, the rate of input we have derived to be KLa CO star minus CO2, okay, which is if you multiply this by the concentration, you get CO star minus CO2. This is on a volumetric basis, this is on a mass basis. Therefore, we need to multiply it by the volume of our system to get on a mass basis. So, KLa CO star minus CO times V. What we called as DO is nothing but CO2. Okay, this is the concentration of oxygen in the medium that is being measured at any time, the accumulated amount of oxygen, and that is our DO. Right? This is the relationship between concentration and DO. Okay. KLa estimation, KLa is an important parameter for the bioreactor, and it needs to be estimated quite often till we are sure that we have a good handle on the KLa. In fact, every time I used to run my bioreactor while I was doing my doctoral studies, I used to estimate KLa just before running my bioreactor every time. So, industry, you need to have a very good estimate of the KLa, because that gives you a direct measure of the oxygen transfer capacity of your bioreactor. There are some methods that exist to estimate KLa in bioreactors. It needs to be estimated at the conditions of cultivation and fermentation, because it's a function of so many different things: temperature, pressure, composition, the flow rate, the agitation rate, and so on and so forth. So many things affect the KLa. Therefore, what we do is we fix all those and then finally estimate the KLa. There are two methods, one older and one slightly newer. Both are equally old. One is the sulfite oxidation method for KLa. The other one is called the dynamic response method. The dynamic response method is the one that is most preferred. So, this being an introductory course, let us talk about this most common method, the dynamic response method. Let us, for the background to this method, let us again look at mass balance on oxygen over the system, broth minus bubbles. This is our mass balance here, Ri minus Ro plus Rg minus Rc equals the accumulation rate, input, output, generation, consumption on oxygen, written on oxygen over the system, broth minus bubbles. Output rate was 0 because of our conveniently chosen system, broth minus bubbles. The generation rate is 0. There is no reaction that is generating oxygen in this case. The input rate we just saw was KLA into CO star minus CO2, CO2 star minus CO2 times V. And if cells are present, then the consumption rate can be given as QO2 times the cell concentration into the volume equals the accumulation rate. I'll tell you what QO2 is. Probably QO2 is the oxygen consumption rate per cell concentration per cell concentration. On a cell concentration basis, this is the oxygen consumption rate. Therefore, you need to multiply it by the cell concentration to get mass per volume per time, and then you need to multiply it by the volume to get mass per time. Okay, this is on that basis. The specific oxygen consumption rate is the name for QO2. We will probably look at that later. Maybe it's not very relevant for KLA. If needed, we'll take a look at that. When no cells are present, X is 0, right? Cell concentration is 0, and at constant volume, V is a constant, right? So this term completely goes away when no cells are present, and the volume is a constant, so you can take it out of the derivative here, V dCO2 dt, and the left hand side just has KLA CO2 star minus CO2 times V. Now we can cancel these two V's, and therefore KLA is CO2 star minus CO2. KLA into CO2 star minus CO2 equals d concentration of CO2 dt. Okay. This gives us the basis for the dynamic response method. The dynamic response method is carried out in the absence of cells. The KLA is estimated in the absence of cells. In the actual broth, that's okay, but there are no cells that are present. So if you solve that differential equation, some details of the solution are given. We are taking appropriate terms to their sides. dCO2 divided by CO2 star minus CO2 equals KLA dt. And from the table of integrals, because this is of the form dx by a constant minus x, right? So you need a table of integrals to solve this, otherwise we'll be reinventing the wheel and so on. So let us use the table of integrals. Dx by a minus x, which is of this form. This is straightforward. KLA dt is a straightforward thing. The solution is natural log C star, or CO2 star is what I call a C star. C star by C star minus CO2 is KLA times T. Thus a plot of C star divided by CO2 C star minus CO2, the logarithm of it, versus time will give us KLA as a slope. You can look at this as y equals mx, where m is KLA, and if we have data from an experiment that gives us the variation of the concentration of oxygen in the liquid versus time, we will get KLA as the slope. That is what is done. That is the experiment that is performed to find KLA of the bioreactor. So a typical experiment is something like this. We have a DO scale here, a time scale here. If initially, of course, the broth is going to contain oxygen because it is exposed to air, filtered air or sterilized air, so we make sure there are no organisms. So we first need to remove all the oxygen from the broth. To do that, we use nitrogen. We bubble nitrogen through the broth. Nitrogen physically strips the broth of all the oxygen, and if you follow the dissolved oxygen level with time after nitrogen is introduced, then it drops down to 0, right, after some time. Make sure that it is at 0, okay, definitely at 0 by seeing a 0 reading for a while, and then if we introduce air, it is going to be something like this. The dissolved oxygen is going to increase and reach the saturated value of dissolved oxygen. We are starting at slightly less than saturation here, which is the usual case. And from this, we could get the data for this kind of a plot. If you look at this, this assumes that the log of C star by C star minus CO2 is a straight line. So this is valid only in the region where this graph is a straight line. So we choose the region where this graph is a straight line and then take the slope of it. That's how we find KLA. I'll give you an example to feel comfortable with it. The DO probe, the probe that is used to measure the dissolved oxygen level, for a picture you could visit this site. I think it is also given in your the notes. It is an electrochemical probe. Therefore, you have a cathode which is silver, an anode which is platinum. Or let me show you that site before we go forward. You know, this is the DO probe. This is a picture of the probe that you could see there. And this also for DO, which uses an optical principle. Probably we'll look at that later. So 25 and 26 are what we are looking at. So a cathode silver, an anode platinum. It's an electrochemical probe, so you need a cathode and an anode and an electrolyte. The electrolyte happens to be potassium chloride, KCl. These are all enclosed in a small chamber surrounded by an oxygen permeable membrane. Okay, you have a cathode, you have an anode in some form, and then you have the electrolyte and an oxygen permeable membrane. And this is dipped into the medium. So oxygen from the medium passes through the membrane and reacts at the cathode as follows. Oxygen giving you hydroxyl ions in the presence of platinum, which is the anode. At the cathode. Okay, I'll clarify that a little later. At the anode, you have silver plus. Okay, this is the silver plus chloride, giving you silver chloride plus electrons. These are the two reactions that take place at the electrodes. Let me say that for now. At the electrodes, when there is electrons being transferred at the electrodes, if you connect the electrodes with a wire, you would see a current. The current produced is proportional to the flux of oxygen across the oxygen permeable membrane, which in turn is proportional to the dissolved oxygen. That's the principle here. Okay, so you have the cathodic reaction, you have the anodic reaction. I think this has been switched around, don't worry about it. And then this is the principle here of the electrochemical probe. There are other optical probes too. I've shown you an link to this optical DO sensor, which is a video. You can look at the video to find that out. Let us finish this lecture with this practice problem 4.1. We will solve this problem in the next lecture. This is a problem for practicing the measurement of KLA. The following data was obtained during KLA determination of a stirred tank bioreactor operating at 500 RPM, 1 atmosphere pressure and 37 degrees C by the dynamic response method. The source oxygen was air. A millivolt meter was used to read the dissolved oxygen level. Find the KLA of the bioreactor given this data. This is the typical data that one gets. I think this is from my own experiment with the bioreactor during my doctoral days. Time versus DO, time in seconds, DO in millivolts. You have these various values. This is the data that is given. You're asked to find the KLA. Please go ahead and do this. We will meet in the next lecture and we will solve this problem.